Hello, everyone. My name is Mahdi, and I'm presenting MATE, multi-attribute table extraction. Assume that we would like to predict the air pollution in Berlin on 23rd of July. This is the data set at hand, and pollution index the target that we would like to predict. City and date are the features that we would like to learn from. We train a model based on the data set at hand, and we would like to predict the data, unseen data. As you see, based on the previous pollution indices 11, 12 in Berlin, the new predicted value is also 12. But the actual pollution is 83 in Berlin on 23rd of July. Daniel Kahneman calls it the turkey incident because as a turkey, you expect every day somebody feeds you, takes care of you. The air pollution is always 12, but then Thanksgiving happens, or in this case, CSD Berlin happens that causes air pollution in the city. So because we already trained on only two features that didn't have enough information to be able to predict the actual air pollution, one solution is to enrich the dataset at hand with additional features, such as events. We use join discovery to this end, and where a user provides a data set and a query column that is basically the join key. And from a large corpus of tables that we call data lake, we find the joinable tables and then feed the machine learning model with the integrated join tables with the input data set. The problem happens when the input data set has a composite key, because the state-of-the-art join search algorithms are all limited to unary keys or single attribute keys. Also, the inverted indices we can only query inverted indices using one single cell values. Therefore, a multi-attribute solution is needed. One naive solution is to select one of the columns of the composite keys and then run the unary join search, and in the end filter the joinable tables based on those single columns. The problem is this solution will lead to a large number of false positives. As you see, this solution can lead up to 4 million tables, where we only have 1,500 tables that contains the information about city and date. Another solution is to have multi-attribute inverted index, where we can query the inverted index with multiple values, and the inverted index returns the location of those values inside the corpus. And then we can find these joinable tables. The problem is these multi-attribute inverted indices require all combination of the values, and that will lead to exponential storage complexity. So the main idea is that given a join key, composite join key, and a candidate table, we have an oracle that can tell if these keys happen in that specific candidate row. If there is a match, we can consider this table as a candidate joinable table. So therefore, we use a single attribute inverted index, where in addition to the location, we enrich this index with an additional oracle information to be able to find out if a specific composite key exists in this specific table, in this specific row. Therefore, because we use single attribute, we have low storage complexity. We can use multi-attribute join discovery, or in general data discovery, and also it is not dependent on the size of the composite key. Assume that this is a sample row from a sample table in data lake. So we would like to create that oracle. We call this oracle the super key, and the requirement to create the super key is a hash function. In our paper, we propose Zash, a novel hash function that enables us to create these super keys. Zash hashes each single value, cell value, into their corresponding hash results, and we aggregate them using bitwise OR operation to create the super key. You can see an example on the right-hand side of the screen. So how do we query these super keys? Assume that this is a join key. So we go through the exact same process to create a super key. We call the super key a query super key, and then we can easily compare it with the actual candidate super key instead of comparing all the single values together. So therefore, on the right-hand side, you see an example that we create the query super key, and then we can easily compare it to the candidate super key. To do that, we can do another OR operation, bitwise OR operation, and see if the value changes, the super key value changes. If it does change, it means that either the value Berlin or July 22nd did not happen in the candidate row, so it is not a joinable row with the given query. But in this case, it didn't change, so this row can be considered as a candidate match. The good thing about the super key is that we only calculate these hash functions only once, and then we can query as many times as we want. The filtration process uses a single logical operation, which is quite fast, and it does not lead to any false negatives. Zash maps each cell value to a bitwise binary representation of the hash result. So the goal of Zash is not only to hash the values from different columns to different hash values with no collision, but also it would like the goal is to minimize the overlap between the bits. So we'd like to decrease the overlap between the bits of each hash function using Zash. Also, our hash function tries to use minimum number of 1 bits, because if we have many 1 bits in our hash result, aggregating them will result to very similar super keys. So how we generate these hash values? Zash requires or leverages 3 different features. First, rare characters. Because the hash space is very limited, so we cannot use all of the characters to encode them. So we use the rare characters that are not frequently used inside the cell values. Then we turn the corresponding bits to those characters to 1 in our hash space. The second feature is character position. If 2 cell values have the similar characters, their position would be the differentiating parameter. In this case, Berlin and November both have character R, but their location are different. So we would like to encode this relative location. To do this, we consider more than 1 bit per character. And doing that, we are able to encode this location of characters inside the cell value. For instance, in Berlin, R happens in the middle, so we turn the middle bit into 1. So if the characters are similar and also their locations are similar, as we see in this example, we encode also the value length. The value length is a differentiating feature where everything else is very similar to each other. So we have character features on the right-hand side, and we also have, we add a length set of bits to our hash space. So we can encode the length of the cell values. Experimental setup. So the data lakes that we use is the Dresden Web Table corpus and also German Open Data. And for each of them, we have 450 query tables to find the joinable tables. In the paper, we have more data lakes and query tables, so feel free to check our paper for more experiments. The first experiment compares Mate to other state-of-the-art baselines with respect to runtime. We have two main category of baselines: multiple join, where it runs join discovery multiple times and finds the intersection of the tables as the multi-column join. And join and filter runs the joinable join search on one column and then filters the result based on the other one. The baseline that has Josie on their name uses the state-of-the-art join discovery algorithm called Josie. And as you see, we outperform both systems, especially in web tables that is way larger and the reading time from the disk is very high. So we see that Mate outperforms both in both cases. We said that Zosh doesn't lead to false negatives, but it leads to false positives. So we compare our hash function to other baselines such as SimHash, Bloom filter, or LessHash Bloom filter, which is a state-of-the-art version of Bloom filter that uses less number of hash functions. And as you see, Zosh in most of the cases outperforms the other baselines. The bold letters represent the best performing algorithm in each cases. We have more also hash functions in the paper, so I recommend you to go back and check our paper. In the end, as a summary, we introduced Mate, a join discovery system that uses a newly developed hashing algorithm that allows us to discover multi-attribute joinable tables to a given input table. And in the end, I would like to say that also Mate is compatible with the traditional filtering approaches that is mainly using the state-of-the-art join discovery systems such as Prefix Filter. Thank you very much.